In this video, we're going to focus on chemistry. We're going to go over some of the basic topics that you need to know if you're about to take a course in chemistry. So let's begin. Let's start with the periodic table. So you need to know the names of the elements, the groups, and some of their properties. So in the first column, you have H, which represents hydrogen, and then lithium, sodium, potassium, rubidium. Now, hydrogen is a nonmetal, but the other ones below that, the lithium, sodium, potassium, rubidium, and even cesium, those are known as alkali metals. The alkali metals are the most reactive of the metals in the periodic table. If you, let's say, put sodium in water, it will react violently. Now, the elements in this row, they all have one valence electron. Therefore, they like to form ions with +1 charges. Now, in the next column, we have elements such as beryllium, magnesium, calcium, strontium, barium. These are known as the alkaline earth metals. These metals are reactive as well, but they don't react as violently as the alkali metals. Now, the alkali earth metals, they have two valence electrons. The valence electrons are those electrons that are in the outermost energy level of an atom. The inner electrons are known as the core electrons. The alkali earth metals, they like to form ions with a +2 charge. Metals, they like to give away electrons. As they release electrons, they will form a positively charged ion known as a cation. The vertical columns are known as groups in the periodic table. So the alkali metals is group 1A. The alkali earth metals is group 2A. The rows are the period. This is period 1, period 2, period 3, and so forth. And next to potassium and calcium, you have the transition metals. You have scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. Below copper, you have silver and gold. Below zinc, you have cadmium and mercury. Mercury is Hg. Next to silver, you have palladium and platinum. These are some common elements that you want to know the name of. Now, the transition metals, they have variable charges. At least most of them do. For example, iron can be in the +2 or +3 oxidation state. Copper is typically +1 or +2. So they have variable charges. But some of the transition metals, like zinc, have a common charge of +2. 99% of the time, zinc has a charge of +2. Same is true for cadmium. Silver is usually +1. Gold could be +1 or +3. Mercury could be +1 or +2. So you need to know the charges of some of these ions. Cobalt is usually between +2 and +3. Manganese could vary from +2 to +7. Chromium, typically as a monatomic ion, +2 and +3. So those are the transition metals. So let's say this is the transition metal area. Over here you have group 1 and group 2. Then in this region you have the inner transition metals. The top part is known as the lanthanides. And the group below that represents the actinides. And then you have the elements on this side, which we're about to go over. So groups 1 to 2A and groups 13 to 18, these are known as representative elements. Group 3 to 12 is the transition metals, and then this is the inner transition metals, which are non-representative elements. Now let's focus on groups 13 to 18. Group 13 is also known as Group 3A. And the elements in this group are boron, aluminum, gallium, indium, and thallium. Next to boron, you have carbon, and below that, silicon, germanium, tin, and lead. This is group 4A. The group 3A elements, they have 3 valence electrons, and most of them like to form +3 charges. For example, aluminum likes to form a +3 charge ion. Same is true for gallium, but gallium I've seen the +1 and +3 state. For indium, it can be +1 or +3, and the same is true for thallium. But aluminum usually doesn't form the +1 ion. It's, for the most part, +3. Now, for the group 4 elements, silicon, for example, can have a +2 or +4 oxidation state. These elements have 4 valence electrons. Germanium, tin, and lead, you'll see that they can also have a +2 charge or a +4 charge. Next, we have nitrogen, phosphorus, selenium. Not selenium, I take that back. Below phosphorus is arsenic, Sb is antimony, and Bi is bismuth. So make sure you know the names of the elements, because typically that's your first quiz in a regular chemistry course. So this is group 5A. These elements, they have 5 valence electrons. However, they like to form -3 charges. These are the nonmetals, at least most of them are. Nitrogen likes to form a -3 charge, and the same is true for phosphide, or phosphorus. As an element, it's called phosphorus, but when it has a -3 charge, it's called phosphide. N, as an element, is called nitrogen, but as an ion with a -3 charge, it's called nitride, with the IDE ending. The next group, group 6A or group 16, these elements, they have 6 valence electrons, and they like to form ions with a -2 charge. Negatively charged ions are known as anions. So we have oxygen, sulfur, selenium, telluronium, and polonium. These are known as the chalcogens. Next to that, you have the group 7A elements, or group 17, and you have fluorine, chlorine, bromine, iodine, or iodine, and acetine. So these have 7 valence electrons, and they like to form -1 charges. So as ions, it's fluoride, chloride, bromide, and iodide. O with a negative charge, or -2 charge, is oxide, sulfide, selenide, and so forth. The halogens are the most reactive nonmetals. As we said before, metals, they like to give away electrons. So metals they form good reducing agents. Nonmetals like to accept or acquire electrons. So nonmetals are usually good oxidizing agents. Nonmetals like halogens are very, very reactive. Fluorine is the most reactive nonmetal. Francium is one of the most reactive metals, which is on the other side of the periodic table. Below cesium, the alkaline metal, you have francium. Because fluorine really wants to have electrons, it is electronegative. Electronegativity increases towards fluorine. So as you go up and as you go to the right, electronegativity increases. So what this means is that fluorine has a very strong desire for electrons. Fluorine's desire for electrons is greater than that of oxygen and chlorine. So nonmetals tend to be electronegative. Metals are usually electropositive. Electronegative elements, once they acquire the electrons that they want, they form negative charges. Electropositive elements like metals, they like to give away electrons, and they're going to develop a positive charge. Now, group 8A, or group 18, this represents the noble gases. So, Over here you have helium. Helium has 2 valence electrons. It doesn't have 8. The first row elements, they can only have a maximum of 2 electrons in their first energy level. Elements in the second row can have up to 8 electrons in their energy levels, or in their second energy level. Neon has 8 valence electrons. And then below neon, you have elements such as argon, krypton, xenon, and radon. The noble gases are chemically inert. They're very stable. They don't really participate much in chemical reactions. So if you get a test question and ask you which element is non-reactive, carbon, nitrogen, fluorine, or neon, your answer is neon. Now let's say if you get a question that asks you which of the following elements is or shares the same chemical reactivity, or is most similar chemically speaking. Let's say if you have nitrogen, oxygen, sulfur, fluorine, and neon. Whenever you have 2 elements in the same column, they share similar chemical properties. So in this case, oxygen and sulfur are chemically similar because they're both chalcogens. They're in the same column. So fluorine and chlorine are chemically similar to each other. They're both halogens. They have the same number of valence electrons, and so their chemical reactivity is similar. Now you need to know where the metals and the nonmetals are with respect to the periodic table. So if you look at a typical periodic table, you're going to see like a line which goes like this. To the lower left of that line, you have metals. On the upper right side, you have nonmetals. So elements like oxygen, fluorine, sulfur, chlorine, these are all nonmetals. But elements like indium, gallium, lead, aluminum, those are metals. And then in between you have metalloids. The most 2 common metalloids that you'll see in chemistry are silicon and germanium. Those are the most common metalloids that you'll be tested on. Metals conduct electricity. Metals can also conduct heat as well. Metals are malleable. They could be hammered into sheets, and they're ductile. They can be drawn into wires. Nonmetals do not conduct electricity. Metalloids, they conduct a small amount of electricity. Nonmetals are insulators. Metals are conductors. Metalloids, they're conductors but with a very high resistance, or electrical resistance. So metalloids, they conduct only a very, very small amount of electricity. Now, which metalloid do you think conducts more electricity, silicon or germanium? As you travel to the left and down across the periodic table, the elements become more metallic. Metallic character increases this way. So which one behaves more like a metal, silicon or germanium? So carbon, for the most part, is considered to be a nonmetal. Silicon and germanium are metalloids. Tin, think of a tin can. Tin metal, well, tin is a metal. Lead is a metal. So as you go down across the periodic table, the elements are becoming more metallic, which means that the electrical conductivity is increasing. So lead can conduct electricity better than tin. Tin metal can conduct electricity better than germanium. So germanium, even though it's a metalloid, can conduct electricity better than silicon because germanium has more metallic character than silicon. Now carbon has different forms, known as allotropes. Carbon can be in the form of diamond, which does not conduct electricity at all, but diamond is an excellent conductor of heat. Or carbon could be in graphite, which you can find it in pencil lead. Carbon graphite does conduct electricity, so make sure you're aware of that. So the metalloids are silicon, germanium, arsenic, antimony, Te. Boron, for the most part, is considered to be a metalloid, but the most common are silicon and germanium. And now the next thing that we need to go over are the diatomic elements. Hydrogen, in its natural state, doesn't exist as H. Hydrogen exists as H2. It's diatomic. So it exists as a molecule. Nitrogen is diatomic. Then you have oxygen, fluorine, chlorine, bromine, and iodine. These are all diatomic, and this is something you just have to know. Hydrogen is a gas at room temperature. Nitrogen is a gas. Oxygen is a gas. Fluorine is a gas. Chlorine is like a greenish gas. Bromine is a red liquid. And iodine is a purple volatile solid. Iodine, under normal standard temperature and pressure conditions, even though it's a solid, it can sublime directly into a gas. Whenever a substance goes from a solid to a gas, it's known as sublimation. So make sure you know your 7 diatomic elements. Now the next thing that we need to go over are bonds, covalent bonds and ionic bonds. So what exactly is an ionic bond? And what is the difference between a covalent bond and ionic bonds? Consider the reaction between sodium metal and chlorine. So let's say if we have an atom of chlorine as opposed to a diatomic molecule. Sodium has 1 valence electron and chlorine has 7 valence electrons. Now, as we mentioned before, metals, they like to give away their electrons. Nonmetals like to acquire electrons. So sodium is going to give away its 1 electron to chlorine. When sodium loses that electron, it becomes a positively charged cation. Chlorine, on the other hand, now it has 8 valence electrons. And so it becomes a negatively charged anion. Whenever you have 2 like charges next to each other, these 2 will feel a force that repels them. Opposite charges, well, like charges repel, but opposite charges attract. Now sodium, it has a positive charge. Chlorine has a negative charge. So these 2 ions, they feel a force of attraction that keeps them together. It is that electrostatic force of attraction that holds the ionic bonds together. So remember, ionic bonds are associated with a transfer of electrons. They're composed of ions that are attracted to each other, and also, typically, not always, but generally speaking, you can identify them because they contain a metal and a nonmetal. Whenever you mix a metal and a nonmetal together, they react in such a way to form ionic bonds. Now, in a covalent bond, the electrons are shared. For example, let's say if we have 2 hydrogen atoms, each with 1 valence electron. These hydrogen atoms will react in such a way to create a bond. And in this bond, there are 2 electrons. Those 2 electrons are shared between the 2 hydrogen atoms. And so this is a covalent bond since we have sharing of electrons. Now, because the elements are identical, because they have the same electronegativity, this is classified as a nonpolar covalent bond. Because the electrons are distributed equally, it's nonpolar. Now, let's say if we have 2 dissimilar elements, for example, hydrogen and fluorine. Now, these are both nonmetals. 2 nonmetals typically form a covalent bond. Now, hydrogen is going to donate 1 electron to form the bond, and fluorine is going to donate 1. So HF looks like this. Now, fluorine is significantly much more electronegative than hydrogen. So fluorine is going to pull the electrons toward itself. So because the electrons are shared unequally, the bond is going to be considered a polar covalent bond. As fluorine pulls the electrons toward itself, it's going to acquire a partial negative charge. And hydrogen, since it loses some of those electrons, it's going to acquire a partial positive charge. Whenever you have a neutral molecule, but where one side is partially positive and the other is partially negative, you have a polarized substance. You have a dipole. To draw the dipole, the arrow has to point towards the more electronegative atom. The electronegativity of fluorine, if you look it up in the table, most textbooks would say 4.0, and for hydrogen 2.1. Whenever the electronegativity difference, if it's greater than 0.5, or if it's equal to or greater than 0.5, the bond is considered to be polar. If it's less than 0.5, it's usually nonpolar. So whenever you have separation of charge within a molecule, you have a polarized molecule. Now consider this bond between carbon and nitrogen. Do you think this bond is polar or nonpolar? Carbon has an electronegativity value of 2.5, and for hydrogen it's 2.1. Now both of these elements are nonmetals, so we have a covalent bond. We just need to decide if it's polar or nonpolar. The En difference is 2.5 minus 2.1, so it's about 0.4. Therefore, this bond is considered to be relatively nonpolar, since the En difference is not 0.5 or more. So anytime you have a molecule that contains only carbon and hydrogen atoms, automatically you know it's a nonpolar molecule. Now it's time to take a mini quiz. Let's see if you remember what you've learned so far. Classify the following compounds as ionic or covalent. Feel free to pause the video as you work out these examples. So, MgO, magnesium oxide, is it ionic or covalent? Magnesium is a metal. It's found on the left side of the periodic table. Oxygen is a nonmetal. Whenever you have a metal and a nonmetal combined, this is going to be ionic. CO2, carbon dioxide. Carbon is a nonmetal. Oxygen is a nonmetal. When you have two nonmetals, you have a covalent molecule. If it's covalent, typically it's usually molecular. So you can also classify it as a molecular compound. It's composed of molecules. Now what about water? Hydrogen is a nonmetal. Oxygen is a nonmetal, so this is classified as covalent. For lithium chloride, lithium is on the left side of the periodic table, and that's a metal. Chlorine is a nonmetal. Be careful, because hydrogen is on the left side, but hydrogen is not classified as a metal. Hydrogen and lithium are in the same column, but lithium is a metal, hydrogen is a nonmetal. So this is ionic. Fluorine is composed only of nonmetals, so this is covalent. Now, because fluorine is made up of the same element, the bond between those two elements is a nonpolar covalent bond because the En difference is 0. Now the bond between carbon and oxygen, that's a polar covalent bond because the En difference is much greater than 0.5. And between oxygen and hydrogen, that's also a polar covalent bond. Now you need to be careful with the exceptions. For example, let's say if you have magnesium sulfate. What type of bonds are found in this compound? Magnesium has a +2 charge. Sulfate is a polyatomic ion with a -2 charge. So because we have ions, we thus have an ionic bond. The ionic bond is between the magnesium ion and the sulfate ion. As you can see, magnesium is a metal, and sulfur and oxygen are composed of nonmetals. Now, within the sulfate ion, you have covalent bonds. The bond between oxygen and sulfur is covalent. Sulfur is a nonmetal, oxygen is a nonmetal. Both of these elements are found in the upper right corner of the periodic table. So that's a covalent bond between the oxygen and the sulfur. So if you have a compound that contains a metal and a nonmetal, and that also has a polyatomic ion, poly means many. A polyatomic ion is an ion with many atoms. So if you have a metal with a polyatomic ion, it has ionic and covalent bonds. Now, there are some ionic bonds that don't have metals. A good example is the ammonium ion. If you see NH4 with something like ammonium chloride, this is ionic. The NH4 plus ion is a polyatomic ion, and chlorine has a negative charge. So here we have ions with charges. So this is an ionic bond. But within the ammonium ion, the bonds between hydrogen and nitrogen, both of them are nonmetals. So this is a covalent bond. So ammonium chloride has ionic and covalent bonds, but there's no metals. So most compounds that are composed of metals and nonmetals are ionic. But there are some that you have to watch out for that do not contain metals. Now, the next thing that we need to talk about is atomic structure, the structure of the atom. But let's go over some things on a periodic table. So C represents carbon, and if you look at the symbol for carbon, there's two numbers, one above it and one below it. The smaller of the two numbers is the atomic number. The atomic number is equal to the number of protons. Now, for a neutral atom, the number of electrons and protons are the same. For ions, ions are particles with unequal number of electrons, and that's why they have a net charge. The bottom number is the average atomic mass of all of the isotopes of carbon. Now, don't confuse isotopes with allotropes. I'll explain what isotopes are. So this number, let's say if we have the carbon-12 isotope, this is the mass number. The mass number is the sum of the number of protons and neutrons. So an element of carbon has 6 protons. So the nucleus, which contains the protons and the neutrons, the nucleus has a net charge of +6. Protons are positively charged, electrons are negatively charged, and neutrons are neutral. Now, a neutral atom of carbon has 6 electrons. In the first energy level, there are 2 electrons in that energy level. The first level can only hold a maximum of 2. The second level can have up to 8. So the second level contains the 4 electrons that are remaining. So carbon has a total of 6 electrons. Notice that carbon is in group 4A of the periodic table. Therefore, it has 4 valence electrons. The 4 valence electrons are the electrons in the outermost energy level of carbon. The 2 electrons on the inside are known as core electrons. Here's a question for you. In the nucleus of a helium atom, helium has a mass of 4 and atomic number of 2. In this form, it looks like the atomic number and the mass number are switched, but the lower of the 2 numbers is the atomic number. Helium has 2 protons, 2 neutrons. So in the nucleus, the protons carry a plus charge, the neutrons are neutral, and helium only has 2 electrons, which are valence electrons because it only has 1 energy level. Now we know that opposite charges attract. So the electrons and the protons, they're attracted to each other. So the electrons feel a force that keeps it rotating in a circle. Whenever you have a force that directs a particle towards the center of the circle, It's called the centripetal force, and it keeps it rotating in a circle. So even though the particle may be moving to the right, the electron is going to stay in a circle because of the centripetal force, which is caused by the electrostatic force between the electrons and the protons. A centripetal force always keeps an object in a circle. If you think of the moon, why it orbits the Earth, the gravitational force that pulls the moon towards the Earth keeps the moon in orbit around the Earth. And that gravitational force is acting as a centripetal force. I know we'll kind of jump into physics here, but it's a good time to talk about it. Now, if opposite charges attract each other, then like charges must repel each other. So how is it that the nucleus remains intact when you have these two protons that are so close next to each other? Shouldn't they fly apart due to the electrostatic force that wants to push them away from each other? It turns out that there's a strong nuclear force that keeps the protons together, and that must be a very, very strong force. If you split the atom, a lot of energy will be released, which is a nuclear reaction. But the strong nuclear force keeps the protons together inside the nucleus. Now let's go over some examples. Let's say if we have an element of fluorine. Fluorine has an atomic mass of 19 and an atomic number of 9. How many protons, neutrons, and electrons are in this fluorine atom? So let's write some equations. To find the number of protons, it's simply equal to the atomic number. The number of neutrons is the mass number minus the atomic number, and the number of electrons is the atomic number minus the charge. If there was a charge, it would be right here. But if there's no charge, we have a neutral atom, which means the protons and electrons are equal. So the atomic number is 9, which means that fluorine has 9 protons. The mass number is 19, but the difference gives you the number of neutrons. 19 minus 9 is 10, so fluorine has 10 neutrons. The number of electrons is the atomic number minus the charge. Since the atom is neutral, it doesn't have a charge, so it's 9 minus 0. Therefore, there are 9 electrons in this atom. Now, out of the 9 electrons, how many electrons are valence electrons? Fluorine has 7 valence electrons. You can find this number based on the group that fluorine is located in. Fluorine is located in group 7A, which is the same as group 17, and so it has 7 valence electrons. So how many core electrons does it have? The total must be 9, so 9 minus 7 is 2. So fluorine has 2 core electrons, but 7 valence electrons, for a total of 9 electrons. Consider arsenic, which has an atomic number of 33 and a mass number of 75. How many protons, neutrons, electrons, core electrons, and valence electrons are found in an atom of arsenic? So because the atomic number is 33, arsenic has 33 protons. The number of the neutrons is the difference between 75 and 33. 75 minus 33 is 42. So arsenic has 42 neutrons. Now, because we have an atom of arsenic, which is neutral, it doesn't have any charge, the number of protons and electrons are the same. Now, how many valence electrons does arsenic have? So arsenic is found in group 5A of the periodic table, so therefore arsenic has 5 valence electrons. So how many core electrons does it have? So 33 minus 5 is 28. Therefore, arsenic has 28 core electrons. So the core electrons plus the valence electrons must add to the total number of electrons. Now let's try another example. Aluminum has an atomic number of 13 and a mass number of 27. and we're going to focus on the aluminum plus 3 cation. How many protons, electrons, and neutrons are found in this particular ion? So the atomic number is 13, therefore it contains 13 protons. The difference between the mass number and the atomic number, 27 minus 13, is 14, so it has 14 neutrons. Now the number of electrons in this ion is the atomic number minus the charge. So 13 minus 3 is 10, so it has 10 electrons. If you add up the charges, we have a charge of 13 from the 13 protons and a charge of negative 10 from the 10 electrons. 13 minus 10 is plus 3, which is the net charge of the ion. Now, what if we have a negatively charged ion? Let's say if we have the phosphide ion, which has an atomic number of 15 and a mass number of 31. How many protons, electrons, and neutrons are in this ion? So because the atomic number is 15, it has 15 protons. The atomic number, or the number of protons, identifies the element. Now, 31 minus 15 is 16, so it has 16 neutrons. To calculate the electrons, it's the atomic number minus the charge. 15 minus negative 3 is the same as 15 plus 3, which is 18 electrons. So if you add up the charges, we have a net charge of positive 15 from the 15 protons and a net charge of negative 18 from the 18 electrons. So the overall charge, 15 plus negative 18, is negative 3. So whenever an ion has more electrons than protons, it has a net negative charge. If it has more protons than electrons, then the overall charge is positive. Now let's go over the different types of isotopes of carbon. The most two common isotopes of carbon is carbon-12 and carbon-13. Chemically speaking, these atoms of carbon behave the same way. They're both elemental carbons. Isotopes, they have the same chemical reactivity, but their nuclear properties are different because the nucleus is different, but the number of electrons is the same and the number of protons the same. Now, how many protons are found in each of these two isotopes of carbon? Both contain 6 protons. To find the number of neutrons is the mass number minus the atomic number. So the one on the left contains 6 neutrons, the one on the right has 7 neutrons. 13 minus 6 is 7. But because these are both atoms of carbon, that means that they're electrically neutral. The number of electrons are the same. So you need to know how isotopes differ from one another. Isotopes, they have the same atomic number, the same number of protons, and they're made up of the same element, in this case, elemental carbon. So that's how they're similar. But how are they different? Isotopes, they differ in their mass number, and they differ in the number of neutrons. So therefore, they're different in their nucleus. So they have different nuclear properties. Carbon-12 is stable, but carbon-13 decays over time. Now, if you look at the periodic table at elemental carbon, you'll see that the mass number is not exactly 12. It's like 12.01. And as we mentioned before, this is the average atomic mass of all of the carbon isotopes. You also have carbon-14, but that's very, very rare. Approximately 99% of carbon atoms is the carbon-12 isotope, and about 1% is carbon-13. So let's say if you have a sample of 100 carbon atoms, 99 of those carbon atoms will be carbon-12, and 1 would be carbon-13. If you have 1,000 carbon atoms, 990 would be carbon-12, 10 would be carbon-13, since 1% of 1,000 is 10. You can calculate the average atomic mass by using a weighted average. The average atomic mass is equal to the mass of the isotope times its relative percent abundance plus the mass of the other isotope times its percentage. Now, if you have a third isotope, it's going to be plus M3P3. And if there's more, this can keep going on forever. But we can calculate the average based on those two isotopes. The mass of the first carbon atom, carbon 12, is 12. The percentage is 99%. 99% as a decimal is 0.99. To convert percent to a decimal, divide it by 100, or simply move the decimal point 2 units to the left. Now, carbon 13 has a mass of 13, but a percentage of 0.01. So if you multiply 12 by 0.99, you're going to get 11.88. If you multiply 13 by 0.01, it's going to be 0.13. And if you add 0.13 plus 11.88, you should get 12.01, which is the average, or the weighted average atomic mass of all of the carbon isotopes that are naturally found on Earth. Now, what about boron? Boron has an average atomic mass of 10.81, and it's element 5 on the periodic table. Now, boron has two principal isotopes, boron 10 and boron 11. Notice that the average is between 10 and 11. So if you have the two isotopes and the average atomic mass, how can you use that information to find the relative percent abundance of these two isotopes? So in nature, or on Earth, what percentage of boron atoms is the B10 isotope, and what percentage is the B11 isotope? So we're going to start with the same equation. So the average is equal to M1P1 plus M2P2. So the average is 10.81. The mass of the first isotope is 10, and the percentage, we're going to call it X. Now, it's important to understand something. Let's say if the B10 isotope is 70%. That means that 30% is boron 11. So if X corresponds to 0.70, then 0.30 must be 1 minus X, because 1 minus 0.70 is 0.30. So notice that X plus 1 minus X adds up to 1, and 1 represents 100%. M2 is the mass of the second isotope, which is 11. And as we mentioned, the percentage is going to be 1 minus X. So we need to solve for the value of X. So it's going to be 10X, and if we distribute the 11, 11 times 1 is 11, and 11 times negative X, that's negative 11X. So now we need to add like terms. So the two like terms are 10X and negative 11X. 10 minus 11 is negative 1, or simply negative X. And now at this point, we need to subtract both sides by 11. And now let's make some space. (10.81) minus 11 is negative 0.19. Those two numbers cancel, so negative 0.19 is X. If you multiply both sides by negative 1, X is 0.19, which corresponds to 19%. Now, X was associated with the B10 isotope, so we have 19% of boron 10. 100 minus 19 is 81%, so that is the relative percent abundance of the other isotope, B11. So notice that we have more of the B11 isotope than boron 10. And it makes sense because the average is closer to 11 than it is to 10. 10.81 is closer to 11, so we have more of the boron 11 isotope. So this is how you can calculate the relative percent abundance of an isotope. within an element. What we're going to do now is have a pop quiz on the properties of the elements in the periodic table. So consider the following elements: iron metal, magnesium, bromine, aluminum, and lithium. So which of the following is a transition metal? What do you think the answer is? Fe is a transition metal. It's between groups 3 and 12. Now, which of the following elements is the most reactive metal listed here? The most reactive metal is typically an alkali metal, and lithium is the only alkali metal in this group. Lithium is found in the first column of the periodic table. Now, which one is a nonmetal? Which element is found in the upper right corner of the periodic table? This is bromine. Bromine is a nonmetal. Now, which of the following elements is an alkaline earth metal? Magnesium is an alkaline earth metal. It has 2 valence electrons, and it's in the second column of the periodic table. Now, which of the following elements has 3 valence electrons? Is it Fe, Mg, bromine, aluminum, or lithium? It turns out aluminum, which is found in group 3A or group 13, has 3 valence electrons. Consider these elements: zinc, bromine, silicon, iodine, and fluorine. Now these are diatomic. Which of the following elements is a liquid at room temperature? Is it zinc, bromine, silicon, iodine, or fluorine? Bromine is a red liquid. Now, which of the following elements has the greatest electrical conductivity? It turns out zinc has the greatest electrical conductivity because it's the only metal that's listed here. Now, which of the following elements is a metalloid? Silicon is a metalloid. It's used to make solar cells, which convert light energy into electricity. Now, which of the following is a solid at room temperature? Iodine is a purple solid. And which one is a gas? Fluorine is a gas at room temperature. Consider these elements as well: argon, uranium, chromium, iron metal, and sulfur. Well, let's write sulfur as S8. So which of the following elements is attracted to a magnet? Which element can be magnetized? It turns out iron metal is ferromagnetic, thus the symbol Fe. Iron metal, if you put it next to a magnet, it's going to stick to the magnet. Now, which element in its ionic form forms colored solutions, particularly different colors? Most transition metals will form colored solutions, but the most common one is chromium. Chromium has multiple oxidation states, and it forms a variety of colors. Now, iron metal is a transition metal, so it too can form a variety of colors. But chromium takes it to another level. Chromium has a lot more colors than Fe. Now, which of these elements is an inner transition metal? Uranium is an inner transition metal. It's part of the actinide series. Now, which of these elements is chemically inert? It doesn't really participate in chemical reactions. The answer is argon. Argon is a noble gas, and the noble gases are chemically stable. They don't like to participate in chemical reactions. They have no need of gaining or losing electrons. Which element is a yellow solid at room temperature, but when melted, it turns into a blood red liquid, and when burned in the presence of oxygen, it produces a blue flame? Which element is that? This element is sulfur. Now consider these other elements: mercury, gold, chlorine, carbon, and germanium. Which of the following elements is a liquid at room temperature? Mercury is a liquid at room temperature. It's called quicksilver, and it conducts electricity as any metal. Now, which of the following elements is known as a noble metal? Gold is a noble metal. It's very difficult to oxidize. It's chemically stable as gold for the most part. Most of the precious elements, or the precious metals like palladium, silver, platinum, these elements are known as noble metals. They're very stable, chemically speaking. They're very resistant to corrosion, and they're very expensive too, those noble metals. Now, which of the following elements does not conduct electricity? Is it mercury, gold, chlorine, carbon, or germanium? The only one that doesn't conduct electricity is the nonmetal chlorine, which is diatomic as Cl2. All of the other elements can conduct electricity. Mercury is a metal, so it can conduct electricity, and gold is a metal too, so gold can conduct electricity as well. Germanium is a metalloid, and so it can conduct a small amount of electricity. Carbon is a nonmetal, but it has different forms, different allotropes. The diamond form of carbon does not conduct electricity. However, the graphite form of carbon does conduct electricity. So the only element that does not conduct electricity is elemental chlorine. Now, which of the following elements is a gas at room temperature? This would also be chlorine. Chlorine is a gas at room temperature. So make sure you know some common properties of the elements in the periodic table. You might see them on your next exam. Here's a question for you. Helium. Is it composed of atoms, molecules, or compounds? And what is the difference between an atom and a molecule? Helium, like all the other noble gases, are composed of atoms. So helium looks like a single particle. It's made up of a single atom. Hydrogen gas is a molecule. A molecule is made up of two or more atoms. It's an individual particle that has multiple atoms. Water, for example, is a molecule and a compound at the same time. So water contains an atom of oxygen and two atoms of hydrogen. So it looks like that. So helium is composed of atoms. Hydrogen is made up of molecules. A molecule is composed of two or more atoms. It could be the same type of atom or different atoms. Water is also classified as a molecule because it contains more than two atoms. But also, water is known as a compound. A compound is a substance that contains two or more different types of atoms or two or more different elements. Water is a compound because it contains hydrogen and oxygen. H2 is not a compound because it contains only one type of element. So H2 is classified as a pure element. It consists only of elemental hydrogen. Water is not a pure element. It's made up of two different types of elements. Helium is a pure element. It's only made up of helium atoms. Now what about sodium chloride? How would you classify it? And let's compare it to water. Sodium chloride is a compound because it has two different elements. But this is not a molecular compound. This is known as an ionic compound because sodium chloride is composed of ions. Whenever you see a metal and a nonmetal, it's usually ionic. Water is a compound as well, but it's also a molecule, so it's a molecular compound. So water is composed of individual particles, whereas sodium chloride, it's a giant crystal that contains many ions. You have sodium ions, chloride ions, and you have billions of these ions together in a solid. So you have a huge network of ions bonded together. But in water, you have individual particles, which makes it a molecule. So here's a quiz for you. I'm going to give you a list of substances, and I want you to identify them as being a molecule, a pure element, being composed of atoms, ionic compound, or molecular compound. So we have CO2, argon, magnesium sulfide, zinc metal, and F2. So let's start with CO2. How would you classify it? So this substance is composed of two nonmetals. So this is going to be a molecule since it's composed of many atoms, but it's also a compound because it's composed of different elements. So it's a molecular compound. Now what about argon? Argon is a noble gas, so it's made up of atoms, and it's also a pure element. We only have one type of element in this substance. Magnesium sulfide. This is composed of a metal and a nonmetal. So it's ionic, and it's a compound, so it's an ionic compound. Anytime you have a compound, it's never going to be a pure element. Zinc is composed of atoms, but these atoms are covalently bonded to each other. And zinc is a pure element. We only have one type of element in this substance. Fluorine is a pure element, but it's also a molecule because it's an individual particle that is composed of two atoms. So now you know how to classify substances. And now what is the difference between a pure substance and a mixture? A mixture is the combination of two or more pure substances. For example, if you mix water, which is a pure substance, with sodium chloride, you have a mixture, a salt-water mixture. If you mix hydrogen with helium, you now have a mixture. So a mixture is simply the combination of two or more pure substances. Sodium chloride is a pure substance. Even though it's a compound that has two different elements, it's still classified as a pure substance. A mixture can be separated into its components by physical means. So for example, you can separate water from salt water by evaporation. That's a physical process. But you can't separate sodium from chlorine in salt by evaporation or by boiling or by some physical process. At least not under practical conditions. So therefore, sodium chloride is not a mixture. You can't separate sodium from chlorine using common physical processes. You have to use a chemical process to separate the atoms within a compound. So remember, a mixture is simply the combination of two or more pure substances. So individually, H2 is a pure substance, helium is a pure substance, but combined, it's a mixture. So whenever you see this plus, it's going to be a mixture. Now, there's two types of mixtures that you need to be familiar with: homogeneous mixtures and heterogeneous mixtures. Consider the two mixtures. Let's say if we have a saltwater solution, where we have free-flowing sodium and chloride ions in water, and on the right side we have an oil-water mixture. Now we know that water and oil don't mix. Typically, oil is less dense than water, and so it floats on top. Which one is homogeneous and which one is heterogeneous? The saltwater mixture is the homogeneous mixture because the salt water is distributed uniformly throughout the solution, and so it's homogeneous. If you look at it, you'll see one clear, distinct solution. On the right side, we have a heterogeneous solution. You can clearly see two distinct phases. You can see the oil and the water separately from each other. Because they don't mix very well, they don't mix evenly or at all, it's heterogeneous. So let's say if you have water and you have sand in the water. Is it homogeneous or heterogeneous? So notice that the sand is not evenly distributed throughout the water. You can clearly see two distinct phases. You can literally see the sand and the water separate from each other. This is a heterogeneous mixture. Now what about air? Is air a homogeneous mixture or a heterogeneous mixture? Air is a mixture of gases. Air contains mostly nitrogen and oxygen gas. About 78% of it is nitrogen and 21% is oxygen. The remainder are gases like argon, CO2, water vapor, and some other stuff. But these gases are evenly distributed throughout air. They're mixed with each other in an even ratio, so to speak. So for example, let's say if you have a room. The composition of air in this region is 78% nitrogen, 21% oxygen. And in this region, it's not going to be 50% nitrogen and 50% oxygen. It's always going to be 78% nitrogen, and 21% oxygen. The distribution of these molecules is even throughout this particular room. So therefore, air is a homogeneous mixture. Now let's move on to another topic, that is unit conversion. You need to know that 1 mile is equal to 5,280 feet. 1 mile is also 1.609 kilometers. Feel free to take notes. In 1 kilometer, there are 1,000 meters. 1 meter is about 100 centimeters. And 1 inch is 2.54 centimeters. There's 3 feet in a yard and 12 inches in a foot. 1 milliliter is equal to 1 cubic centimeter, and 1,000 milliliters is equivalent to 1 liter. So these are units for distance. For time, you know that 1 year is 365 days, 1 month is approximately 30 days, a day is 24 hours, an hour is 60 minutes, and a minute is 60 seconds. So these are some common conversions that you want to know. So let's say if you have 460 meters, how can you convert that to kilometers? Now the first thing that you want to do is identify the conversion factor that you need. The conversion factor between kilometers and meters is this. 1 kilometer is 1,000 meters. Now start with what you're given. We're going to write 460 meters over 1. In the next fraction, you need to place the conversion factor, but in the appropriate order. So notice that we have meters on the top left. That means we need to put the unit meters on the bottom right. The number that's associated with meters, or that's next to it, is 1,000. So that 1,000 is going to be right next to the meters. So on top, we're going to put 1 kilometer. So the unit meters cancel, and we're going to get km. So because the 1,000 is on the bottom, we need to divide instead of multiply. So it's 460 divided by 1,000. Whenever you divide by 1,000, simply move the decimal 3 units to the left. So 460 meters is equivalent to 0.460 kilometers. Let's try another example. Convert 75 millimeters into centimeters. The conversion factor is 10 millimeters is equal to a centimeter. So how would you set it up, and what's the answer? So let's start with what we have, which is 75 millimeters. Now, since we have millimeters on the top left, we need to put it in the bottom right. And the 10 is associated with millimeters, so let's put that there. And 1 centimeter is going to go on top. So these units cancel, and it's 75 divided by 10, which if you move the decimal 1 unit to the left, it's going to be 7.5 centimeters. Now let's say if we have a multi-step problem. For example, if you have 0.25 kilometers, how can you convert that into feet? So we know that 1 mile is equal to 5,280 feet, and 1 mile is 1.609 kilometers. So we need to convert from kilometers to miles, and then miles to feet. So how can we do it? Feel free to pause the video and try this example yourself. So let's start with what we're given. Now, in the next fraction, we need to put the kilometers on the bottom so that these units will cancel. And we want to convert it to meters initially. So we know that 1.609 kilometers, this is supposed to be miles, by the way, not meters. 1.609 kilometers is 1 mile. So now we can convert miles into feet. So we got to put the unit miles on the bottom. 1 mile is equal to 5,280 feet. And so the unit miles cancel. And this is going to give us the answer in feet. So it's 0.25 divided by 1.609 times 5280. And you should get 820.4 feet. Now let's say if you have a unit of area, for example, 36 square feet. How can you convert it into square yards? What can we do? So we know the conversion factor. There's 3 feet in a yard. So always start with what you're given. Now, in the next fraction, we need to put feet on the bottom, yards on top. So we know there's 3 feet in 1 yard, but because we have a square here, we need to square it. So we need to divide 36 by 3 2 times, or by 9. 3 squared is 9. So the unit feet squared will cancel, and we're going to get yards squared. So 36 divided by 3 is 12, and 12 divided by 3, a second time, is 4. So it's 4 square yards. This is the same as 36 divided by 9, which is 4. Now let's try another example. Let's say if we wish to convert 5,000 cubic millimeters into cubic centimeters. How can we do it? So this is a unit of volume whenever it's raised to the third dimension. We know the conversion factor is 10 millimeters is equivalent to 1 centimeter. So we're going to put that in the next fraction. Now for this particular example, we need to raise it to the third power. So we need to divide 5,000 by 10 3 times, or by 10 cubed, which is 1,000. 5,000 divided by 10 is 500. 500 divided by 10 is 50. 50 divided by 10 is 5. So this is 5 cubic centimeters. Or you could say 5,000 divided by 1,000 is 5. So now you know how to convert from one unit of volume to another unit of volume. How would you convert 30 meters per second into miles per hour, which can also be written as mph? How can we do it? So notice that we have the unit of speed, which is meters and seconds. We need to put the unit meters on the top of the fraction and seconds on the bottom. Let's make an outline of what we need to do. So we need to convert meters to kilometers and kilometers to miles. And then we got to convert seconds into minutes and minutes into hours. So what's the conversion factor for meters and kilometers? There's 1,000 meters for every kilometer. So the unit meters cancel. And we know that between kilometers and miles, 1 mile is equal to 1.609 kilometers. So kilometers cancel. Now that we have the unit miles, we don't need to change that anymore, since that's what we want. What we do need to change is seconds into hours. So because we have the seconds on the bottom, it has to be on the top. Now let's convert seconds into minutes. There's 60 seconds in 1 minute, and there's 60 minutes in a single hour. So the unit seconds cancel and minutes cancel. So now we can get the answer. So it's going to be 30 divided by 1,000 times 60 divided by 1.609 times another 60. So you should get 67.1 miles per hour. Here's another one. Convert 25 feet per second into kilometers per hour. So let's start with 25 feet over seconds. We know how to convert seconds into hours, but how can we convert feet into kilometers? Let's convert feet into miles, and then we can convert miles into kilometers. If you recall, there's 5,280 feet per mile, and we know that there's 1.609 kilometers in a single mile. So these units cancel, and the unit miles cancel. And we know there's 60 seconds in a minute, and 60 minutes in an hour. So seconds cancel, minutes cancel as well. And so it's going to be 25 divided by 5280 times 1.609 times 60 times 60. And you should get 27.4 kilometers per hour. Now the next thing that we need to do is cover the metric system. You need to know that tera corresponds to 10 to the 12th power. giga is 10 to the ninth power. Mega represents 10 to the 6, which is a million. 10 to the 9 is a billion. Kilo is 10 to the third, which is 1,000. Now, below kilo, you have hecto, which is 10 squared, or 100, and deca, which is 10 to the first, or 10. And below that, you have deci, which is 10 to the minus 1, and then centi, which is 10 to the negative 2, and milli, which is 10 to the minus 3, and then micro, which is 10 to the negative 6, nano, that's 10 to the negative 9, and pico is 10 to the negative 12. Now, from this, you need to be able to write the conversion factor. So, for example, 1 kilometer is 10 to the 3 meters. So you can write it like this: 1 km is 1 times 10 to the third meters. That's your conversion factor. Or if you want to write the conversion factor for micro, you can say 1 micrometer, or UM, is equal to 1 times 10 to the negative 6 meters. So how would you write the conversion factor for millimeters, centimeters, and nanometers? So let's start with centimeters. 1 centimeter is 1 times 10 to the negative 2 meters. If you multiply both sides by 100, you'll get this conversion factor. 100 centimeters is 1 meter. For millimeters, we could say 1 millimeter is 1 times 10 to the minus 3 meters. For nanometers, 1 nanometer is 1 times 10 to the negative 9 meters. So there's always a 1 with the prefix. And on the other side, the multiplier is always associated with the base unit, in this case, meters. Let's try an example. Let's say if we have 170,000 centimeters, and we wish to convert it to kilometers using the metric system. How can we do it? What you want to do is, you want to convert centimeters to meters, and then meters to kilometers. So let's write out the conversion factors. 1 kilometer is 1 times 10 to the 3 meters, which is 1,000 meters. 1 centimeter is 1 times 10 to the negative 2 meters. These are the two conversion factors that we need. So let's start with 170,000 centimeters over 1. Let's convert it to meters first. So the unit centimeters has to go on the bottom, and therefore the unit meters has to go on top, using this conversion factor. So the unit centimeters will cancel, and in the next step we can convert meters into kilometers. So we got to put meters on the bottom and kilometers on top so that these units will cancel. At this point, we could do the math. Now, what's going to happen if we take 10 to the third and move it to the top? X to the negative 2 is the same as 1 over x squared. Whenever you move an exponent from one side to the other side, it changes sign. So the positive 3 on the bottom will become negative 3 when it moves to the top. So we can rewrite this as 170,000 times 10 to the negative 2 times 10 to the negative 3. What is 10 to the negative 2 times 10 to the negative 3? Now, what is x cubed times x to the fourth? Whenever you multiply common bases, you are allowed to add the exponent. So 3 plus 4 is 7. This is x to the 7. So therefore, 10 to the negative 2 times 10 to the negative 3 is 10 to the negative 5. Because negative 2 plus negative 3 is negative 5. So now we need to put the number in appropriate scientific notation. We need this number to be between 1 and 10. So we need to move the decimal point 5 units to the left. 1, 2, 3, 4, 5. If we do that, this is going to increase by 5. Negative 5 plus 5 is 0. So it's 1.7 times 10 to the 0. Anything raised to the 0 power is 1, so the answer is 1.7 kilometers. Another way you can see it is you need to realize that 170,000 is 1.7 times 100,000. And because 100,000 contains 5 zeros, 100,000 is 10 to the 5th. And 5 plus negative 5 is 0. So you get 10 to the 0, which is 1. And so the answer is 1.7 kilometers. Let's try another example. Try this one. Convert 380 micrometers into centimeters. Feel free to pause the video as you work out this example. So let's convert micro into meters and then meters to centimeters. So the first thing you want to do is write out the conversion factors that you need. Micro is 10 to the negative 6, so 1 micrometer is 1 times 10 to the negative 6 meters. Centi is 10 to the minus 2. So these are the conversion factors that we need. So let's start with what we're given, and let's convert micrometers into meters. So we need to put the unit micrometers on the bottom so that they will cancel. And in the next step, we need to put the unit meters on the bottom, which will give us centimeters. So these units will cancel. So now we can do the math. So it's going to be 380 times 10 to the negative 6, and then we're going to take this, move it to the top, so the negative 2 will become positive 2. Negative 6 plus 2 is negative 4. So we have 380 times 10 to the negative 4. Now we need to move the decimal so that it's between the 3 and the 8. The number has to be between 1 and 10. So we need to move it 2 units to the left. Whenever you need to move the decimal point to the left, you need to increase this number by the number of spaces you move to the left. So since we moved 2 units to the left, we got to add 2 to it. So it's going to be 3.80 times 10 to the negative 4 plus 2 is negative 2. So this is the final answer in centimeters. Try this one. Let's say if you have 3.6 times 10 to the 4 kilometers. Actually, instead of kilometers, let's make it nanometers. Convert this number into decimeters. So how can you convert 3.6 times 10 to the 4 nanometers into decimeters? So just like before, we need to go from nanometers to meters, meters to decimeters. So let's write out the conversion factors that we need. 1 nanometer is 1 times 10 to the negative 9 meters. Deci is associated with negative 1, so 1 decimeter is 1 times 10 to the minus 1 meters. So let's start with the number that we have, and let's convert to meters. So we need to put nanometers on the bottom, and we got to put 1 times 10 to the negative 9 meters on top. And so meters will have to go on the bottom in the next fraction so that these units cancel, and we need to put decimeters on top. So let's move this number to the top. So what we have is 3.6 times 10 to the 4 times 10 to the negative 9 and times 10 to the positive 1. So 4 plus negative 9 is negative 5. Negative 5 plus 1 is negative 4. So our final answer is 3.6 times 10 to the negative 4 decimeters. Notice that we don't need to change this number because 3.6 is between 1 and 10, so it's already in proper scientific notation form. Let's try this problem. An 8.4 gram rock was placed in a graduated cylinder that contained 24.1 milliliters of water. The volume went up to 26.2 milliliters. Calculate the density of the rock. The equation for density is mass divided by volume. Now let's understand what's happening here. So let's say if we have a container that has 24.1 milliliters of water. And then we're going to add a rock. So then the volume is going to increase to 26.2. And so here's the rock. What is the volume of the rock? So this is how you can find the volume of the rock. It's by water displacement. The volume of the rock is the difference between these two values. So it's 26.2 minus 24.1, which is 2.1. So the amount that the volume increases by, that's the volume of the rock. And we know the mass of the rock, it's given to us, it's 8.4. And so 8.4 grams divided by 2.1 gives us a density of 4 or simply 4. It's 4 grams per milliliter. Now keep in mind, 1 milliliter is the same as 1 cubic centimeter. So we already have the density in grams per cubic centimeter, which is the answer to the first part of the question. So now we got to find the density in kilograms per cubic meter. So we need to convert it. So what is the conversion between kilograms and grams? 1 kilogram is 1,000 grams. Kilo represents 10 to the third, which is 1,000. And 1 meter is 100 centimeters. So let's convert it. So there's 100 centimeters in a meter, but we need to raise it to the third power because of the 3. And to convert grams to kilograms, there's 1 kilogram per 1,000 grams. So the unit grams cancel, and cubic centimeters will cancel as well. So we have 4 times 100 cubed, which is 100 times 100 times 100, and then on the bottom we have 1,000. So we can cancel 3 zeros, and so what we now have is 4 times 100 times 10, and this is simply 1, which will not change the value of anything. So 4 times 100 is 400 times 10, that's 4,000. So the answer is 4,000 kilograms per cubic meter. Here's another density-related unit conversion problem. The price of gold is $42 per gram. The density of gold is 19.3 grams per cubic centimeter. What is the value of a rectangular gold bar that is 1 by 2 by 3 inches? So what's the first thing we need to do? How can we find the answer to this problem? So notice that we have the length, width, and height of the rectangle. So we could find the volume. So if we were to draw a picture, here's a typical rectangle. So let's say we have a width of 2, a width of 1, height of 2, and a length of 3. The volume of a rectangle is length times width times height. Since we have the volume, which is going to be in cubic inches, we can convert that to cubic centimeters. And using a density, which has grams and cubic centimeters, we can convert it to grams. And using the price of gold per gram, we can convert that to dollars and get the value of this particular gold bar. So let's go ahead and do that. So first, let's find the volume. So length times width times height, 1 times 2 times 3. The volume is 6 cubic inches. So let's convert it to cubic centimeters. Keep in mind, 1 inch is equal to 2.54 centimeters. and we need to raise it to the third power so that cubic inches will cancel. Now that we have cubic centimeters, let's use the density to convert it to grams. 1 cubic centimeter is equal to 19.3 grams based on this number. And the price of gold is $42 per gram. So the unit grams cancel and cubic centimeters. So now we can get the answer. So it's 6 times 2.54 raised to the third power times 19.3 times 42. So this particular gold bar is worth $79,700.12. The next topic in chemistry that we need to talk about is significant figures. So the first thing you need to be able to do is you need to be able to determine the number of significant figures within a number. So for example, 395 has how many significant figures? Any non-zero number is always counted as a significant figure. So we have 3 significant figures. Now what about 407? The only thing you have to worry about is the zeros. This 0 that's between the 4 and 7, is it significant or is it not? In between zeros are always significant. So this is counted as 3 sig figs. Now what about 5050? So we know the 5s are significant and the 0 that's between it. But what about the 0 to the right? The zeros to the right of a non-zero number are known as trailing zeros. Trailing zeros are sometimes significant if there's a decimal point. Since we don't have a decimal point, that particular 0 is not significant, so we only have 3 sig figs. Now if we had 5050 with a decimal point, then this 0 is counted, so we have 4 sig figs. Try these. 40, 400, how many sig figs are in these numbers? So here we have a trailing 0 and there's no decimal point, so we only have 1 sig fig. The same is true for the next one. The 2 zeros to the right are not counted. But now that we have a decimal point, the zeros to the right of the 4 are counted. So this is 4 and this is 6. All of these are counted. Now what about these numbers? 0.01407, 0.0030, 0.057080, 0.0010500, and 0.04000. The zeros to the left, which are leading zeros, are never counted as significant, so we could ignore those zeros. So here we have an in-between 0, which is between the 4 and 7, that's counted, so we have 4 sig figs. The 0 to the right of the 3 is counted because we have a decimal point, so it's 2. For the next one, we have 5 sig figs. Since we have a decimal point, any zeros to the right of a non-zero number are counted. And for this one, we also have 5 sig figs. For this one, we only have 4. Now what about for scientific notation? How many sig figs are there in these numbers? Because we have a decimal point, those two numbers, any zeros to the right will be counted. So this is 2 sig figs. Here we have a total of 3, and here we have 4. And in this number we have 5 sig figs. So in scientific notation, since you're usually going to have a decimal point, the zeros to the right of a non-zero number will be counted. And you don't have to worry about the multiplier. that's not related to sig figs, so you can just ignore it. Now, you need to know how to round a number to the appropriate number of significant figures when dealing with multiplication, division, addition, and subtraction. So let's say if we have 5.38 times 4.1. For multiplication and division, you need to round the final answer to the least number of significant figures. The first number has 3 sig figs, the second one has 2, so the final answer should only have 2 sig figs. So first, let's get the exact answer. 5.38 times 4.1. So the exact answer is 22.058. So how can we round this answer to a number that's close to 22.058 but still has 2 sig figs? So we could say this is approximately 22, which has 2 sig figs. Now let's say if we have 8.946 divided by 4.13. Find the answer and round it to the appropriate number of significant figures. So here we have 4 sig figs, and in this number we have 3. So first, let's get the exact answer, which is 2.1661, and we can stop there. So now we got to round this number to 3 significant figures. So the first 2 numbers are going to remain the same. The last one, the third one, this is what we have to decide. Should we keep it at 6 or should we round it up to 7? To find the answer, look at this number. If it's 5 or more, you need to round up. So the 6 is going to go up to a 7. So we're going to say 2.17. Now you need to understand the rules of addition and subtraction. So let's say if you want to add 4.32, 1 plus 5.6. You need to round to the least number of digits to the right of the decimal point, which is here. So when you add these two numbers, you're going to get 9.921. So you need to round to the nearest 10th place. So we look at this number. Since it's less than 5, we're going to keep it down at 9. If it was greater than 5 or equal to 5, we would round it up to 10. So the answer for this example is 9.9. Now let's say if you have 14.753 minus 2.12. This is going to be 33621. That's the exact answer. But we need to round it at this position to the nearest hundredths place. So since this number is less than 5, we're going to keep this at 3 and not round it up to 4. So the answer is 12.63. So for addition and subtraction, line it up. For multiplication and division, round to the least number of significant figures. Now, the next thing that you need to be able to do is you need to be able to name compounds. So for example, let's say if you wish to write the name of SCl2 and MgCl2, how would you do it? MgCl2 is called magnesium chloride. SCl2 is known as sulfur dichloride. So why is it that SCl2 is sulfur dichloride, but MgCl2 is not magnesium dichloride, it's simply magnesium chloride? Why do we use the prefix di for this molecule, but we don't do it for this one? The reason being is MgCl2 is ionic. It's composed of a metal and a nonmetal. SCl2 is not ionic. It's a molecular or a covalent compound. For molecular and covalent compounds, you need to use the prefixes like mono, di, tri, tetra, and so forth. Mono represents 1, di is 2, tri is 3, tetra is 4, penta is 5, hexa is 6, hepta is 7, octa is 8, nona is 9, deca is 10. For ionic compounds, you don't need those prefixes. So let's go over the nomenclature of molecular compounds. Go ahead and name the following compounds. So this one is called tetraphosphorus because there's 4 phosphorus atoms. Decoxide. Deca is for 10. Now what about this one? Se is selenium. We don't have to say monoselenium. If the first element contains only one atom, simply just write the name of the atom. So this is selenium hexafluoride. The last element ends in IDE. Now here we have 2 nitrogens, so we're going to say dinitrogen pentaoxide, or simply pentoxide. Now let's work backwards. What is the formula for phosphorus trichloride? And also, try these as well. What's the formula for carbon monoxide and silicon tetrachloride? Phosphorus trichloride, so we have a P and we have a Cl, but we have 3 Cl since we have the word tri. Carbon monoxide, so monooxide, that means we have 1 oxygen. Silicon tetrachloride, tetra means 4, so we have 4 chlorine atoms. So for molecular compounds, it's not very difficult to name them or write the formula. You simply need to know the names of the first 10 prefixes, mono, di, tri, all the way to deca. Before we move on to naming ionic compounds, we need to go over the names of common monoatomic and polyatomic ions. So for example, ClO4. This is a polyatomic ion. It's an ion that contains many atoms. Poly means many. This is called perchlorate. ClO3 minus. This is simply called chlorate. Perchlorate compared to chlorate simply has 1 more oxygen. ClO2 minus is called chlorite. 8 usually has 1 more oxygen than ite. And ClO minus is known as hypochlorite. Hypo means below or less. So hypochlorite has 1 less oxygen than chlorite. Cl minus is a monoatomic ion. It's an ion composed of 1 atom. Monatomic ions usually has the suffix "ide." When you see that, there's no oxygen attached to it. When you hear the words 8 and ite, typically that element has some number of oxygens attached to it. SO4 2 minus. You need to know that this is called sulfate. And what do you think SO3 2 minus is called, and S2 minus? Since SO3 has 1 less oxygen than SO4, if SO4 is sulfate, SO3 is sulfite. S2 minus is a monatomic ion, so it's going to have the suffix IDE. So this is called sulfide. What do you think the names for these ions are? PO4 3 minus, PO3 3 minus, P3 minus, HPO4 2 minus, and H2PO4 minus. PO4 3 minus is known as phosphate. So if you know the first one, you could find the rest. PO3 has 1 less oxygen, so if PO4 is phosphate, PO3 is phosphite. P3 minus, this is phosphide with the IDE ended. HPO4 2 minus, this is hydrogen phosphate. H2PO4 minus is dihydrogen phosphate. Now there are some others you need to know. CO3 2 minus, this is known as carbonate. So based on that, what do you think HCO3 minus is? What's the name for this particular polyatomic ion? HCO3 minus is known as hydrogen carbonate, or more commonly bicarbonate. Now what about OH minus, C2H3O2 minus, C2O2 2 minus, and Cn minus? OH minus is known as hydroxide. C2H3O2 minus, this is called acetate. C2O2 2 minus, this is oxalate. And the last one, Cn minus, is known as cyanide. But now there's more. What about CrO4 2 minus, Cr2O7 2 minus, MnO4 minus, O2 minus, O2 2 minus? CrO4, this is called chromate. Cr2O7, that's dichromate. And the next one, MnO4 minus, is permanganate. If you see O2 minus, where the individual oxygen has a charge of -2, this is called oxide. But if you see O2 2 minus, where each oxygen atom has a charge of -1, so two of them has an overall charge of -2, this is known as peroxide. And if you see O2 with a -1 charge, meaning each individual oxygen atom has an oxidation state of -1/2, if you divide -1 by 2, this is known as superoxide. So these are the different forms of oxide, but the most common is just oxide. Peroxide, you may see that occasionally. Superoxide is rare. Now let's go over naming compounds. So let's say if we wish to name NaCl, which is an ionic compound. It has a metal and a nonmetal. So the first element, simply write the name. Na is called sodium. Now the second element, think of the ion that is part of that compound. This is Cl minus, which is called chloride. So the second element has the IDE ending if it's a monatomic ion. So this is sodium chloride. Go ahead and name these elements. MgO, CaS, AlBr3, and let's see, GAN, and finally ZnF2. So MgO, Mg is known as magnesium. And O, the second part, it's a monatomic ion, so it's going to be called oxide. Now what about CaS? Ca is calcium, and for the second element we need to add the IDE ending. So instead of saying sulfur, we're going to say sulfide. Now what about AlBr3? Al is aluminum, and Br, instead of saying bromine, it's bromide. Now what about the next one, GAN? Ga is called gallium, and N represents nitride. So it's gallium nitride. And the last one, Zn, is zinc. And instead of saying F, fluorine for F, it's going to be fluoride. The U comes before the O. Don't put OU, it's UO. Try these. BaSO4. Let's see. LiClO3. KCN. NaOH. Sr3PO42, and MgNO32. So now we have ionic compounds that contain polyatomic ions. If you know the names of the polyatomic ions, it's not going to be difficult. So Ba, you need to know the name for Ba. Ba is called barium. And SO4 is the sulfate ion. So this is simply called barium sulfate. So that's not too bad. So let's try the next one. Li is lithium. And ClO3, as we mentioned before, that is chlorate. So we have lithium chlorate. Now what about the next one, KCN? So what is K? K is potassium, and Cn is another polyatomic ion, and this one is called cyanide. Very dangerous stuff. Now what about NaOH? Na is sodium, and the OH minus ion, that's a polyatomic ion, so that's hydroxide. Now what about the next one, Sr3PO42? The first element is called strontium, and the second one, the polyatomic ion, you simply need to know that it's phosphate. So it's going to help you a lot for the rest of your chemistry course if you commit the polyatomic ions to memory. Because when you're working with math problems, typically you need to know the formula of the compound. So they may give you a name, let's say barium sulfate. You need to be able to write the formula, calculate the molar mass. But if you don't know what sulfate is, you can't do the problem. So it's going to put you at a serious disadvantage if you don't know the polyatomic ions, especially for the rest of your chemistry course. So to put it this way, your grade significantly depends on knowing those polyatomic ions. Your teacher may give you the polyatomic ion sheet on the test, but you'll be able to solve the problems faster if you simply know it. Now what about the last one? Here we have Mg, which is magnesium, and NO3 is nitrate, so it's simply called magnesium nitrate. Now sometimes you may have compounds that have multiple oxidation states, which are basically multiple charges. And for such compounds, you need to specify which charge it has when naming it. And you would do that using the Roman numeral system. So let's go over the Roman numeral system. This number represents 1. This represents 2. We have 2 I's. This is 3. Now, if you see a V, V represents 5. Now, if you see like an I to the left of the V, it represents subtraction. It's like 5 minus 1. So this represents 4. Now, if the I is to the right of the V, it represents addition. 5 plus 1 is 6. So this is 5 plus 2, which is 7. And it's rare that you'll ever need to go past 7. So we'll stop there. Now let's say if we have the formula CuCl2 and CuCl. So how would you name these two compounds? CuCl is copper 1 chloride. CuCl2 is copper 2 chloride. Well, you might be wondering, well, that's not bad. All you need to do is look at the subscript. While generally that's going to give you the answer, it's not always the case. So sometimes this will be the Roman numeral, but you can't always rely on it. This number means that copper has a +2 charge. Now chlorine, as chloride, has a -1 charge, and there's 2 of them. So the net negative charge, or the total negative charge, is -2. And we only have 1 copper ion. So that copper ion has to have a +2 charge to neutralize the 2 negative charges. Now for the one on the bottom, we only have 1 chloride ion. So this copper only needs a +1 charge to neutralize the -1 charge. So because the copper is in a +1 oxidation state, it's copper 1 chloride. Now it turns out there's another way you can calculate the oxidation state of copper, and that is by using an equation. Copper plus 2 chlorine atoms has to have a net charge of 0. Notice that there's no overall charge and its compound is neutral. If there was an overall charge, you'll see like a -2 on the outside or something. So we need to solve for the charge on copper. So let's replace copper with X. And let's substitute -1 with chlorine. Or chlorine with -1, that's what I meant to say. So 2 times -1 is -2. To solve for X, we need to add 2 to both sides. So therefore X, or copper, has an oxidation state or a charge of +2. So that's how you can find it. For the other example, it's going to be Cu plus Cl, which equals 0. So Cl is -1. If you add 1 to both sides, you'll see that copper is equal to +1. So it's copper 1 chloride. Okay, let's try FeS and Fe2S3. So for FeS, do you think it's iron 1 sulfide since the subscript is 1? Or is it something else? So let's find the oxidation state of Fe. Sulfur has a -2 charge, so Fe has to be, or has to have a +2 charge, since they're in a 1-to-1 ratio. If you write the equation, and if you replace S with -2, you'll see that Fe has a +2 charge. So therefore, it's not iron 1 sulfide, rather, it's iron 2 sulfide. So don't always rely on the subscripts. It's a good indication of what it may be, but always double check it. So in this particular case, is it iron 3 sulfide or is it something else? Let's find out. Now let's write an equation. 2Fe plus 3S has to add up to 0. So S has a charge of -2. 3 times -2 is -6. And if we add 6 to both sides, it's going to be 2Fe, which equals +6. So to solve for Fe, we've got to divide by 2. 6 divided by 2 is 3, so in this particular case, Fe does have a +3 oxidation state. So in this case, it is 3. So it's going to be iron 3 sulfide. Now let's try another example. Try these. PbO and SnO2. So even though lead and tin are not transition metals, they do have multiple oxidation states, typically +2 and +4. So you know that oxygen has a -2 charge. That means Pb has to have a +2 charge. Since these two are in a 1-to-1 ratio, that means the charges are the same, even though the sign is opposite. So this is going to be called lead 2 oxide. Now the one on the bottom, let's solve it. So we have Sn plus 2 oxygen atoms equals to a net charge of 0. And each oxygen has a charge of -2. So 2 times -2 is -4. If we add 4 to both sides, tin is in the +4 oxidation state. So this is going to be called tin 4 oxide. So now let's talk about how to write the formula of an ionic compound. So how would you write the formula for lithium chloride? The first thing you should do is write the ions. Lithium, as an ion, has a +1 charge. It's an alkali metal. It has 1 valence electron, and elements in group 1a typically form ions with +1 charges. Chloride is a halogen. It's going to have a -1 charge. If the charges are the same, you can simply write them in the 1-to-1 ratio. So another example of this is calcium selenide. Calcium is an alkaline earth metal with a +2 charge, and selenium is a chalcogen that's below sulfur and it has a -2 charge. Because the charges are the same, you can simply write them in a 1-to-1 ratio. Another example is aluminum nitride. Aluminum is in group 3a of the periodic table, so it has a +3 charge, and nitride is a group 5a element and it has a -3 charge. So here the charges are the same, so you can simply write them as ALN. So that's the first thing that you want to keep in mind. Now what about when the charges are different? So let's say if we have magnesium bromide. Magnesium has a +2 charge. It's an alkaline earth metal. And bromide, a halogen, has a -1 charge. So the charges are different. So in this case, you can use the crisscross method. So this is going to be Mg1Br2. But if you have a 1, you don't really need to write the 1. So it's simply MgBr2. Now what about aluminum sulfate? Aluminum has a +3 charge, and sulfate, this is where you need to know your polyatomic ions, it's SO4 2-. So using the crisscross method, it's going to be Al2 SO4 3. Now whenever you have multiple polyatomic ions, you need to enclose it within a parenthesis. Now what about this one? Sodium phosphate. How would you write the formula for it? Sodium is an alkali metal with a +1 charge. Phosphate is a polyatomic ion, which is PO4 3-. So using the same crisscross method, it's going to be Na3PO4. Now we don't need to write the 1, so we can simply leave it as Na3PO4. Now what about this one? Lead 4 sulfide. Feel free to pause the video and try this example. So in this particular case, the 4 tells us that lead has a +4 charge. Sulfur has a -2 charge, typically. And if we use the crisscross method, it's going to be Pb 2s4. But notice that we have two even numbers, and we don't have the lowest whole number ratio. If you can divide it by a whole number, you should. So if we divide both numbers by 2, it's going to be PB1S2, which we could simply write it as PBS2. So this is the case where the subscript is not always the charge. As you can see, we were able to reduce the subscripts, and that's why these two don't match. Now the next thing that we need to go over is the nomenclature of acids. Whenever you see a hydrogen to the left of a nonmetal, it's an acid. Now there's some things that you need to know. 8 is associated with ic when writing the name of the acid. I is associated with is, and ide will have the prefix hydro and the suffix ic. And for all of these, add the word acid. So let me give you some examples. Well, let's start with H2SO4. So H2SO4 contains the polyatomic ion sulfate. So let's focus on the 8 part. We know we need to replace it with ic. So to write the name of the acid, write the element first, which is sulfur, and then add the suffix ic, and then add the word acid. So this is called sulfuric acid. Not bad, right? Now let's say if we want to name H2SO3. So notice that it contains the polyatomic ion sulfide. So let's focus on the suffix "ite." So we're going to have to replace it with is. So let's write the element first, sulfur, and then let's add the is part to it, and then the word acid. So this is called sulfurous acid. Now what about H2S? So S, or S2 minus, is a monatomic ion, and it's called sulfide. So it has the IDE suffix. So before we write the element sulfur, we need to put the prefix hydro, and then let's write the element sulfur, and then let's replace ide with the suffix ic, and then let's add the word acid. So this is called hydrosulfuric acid. Now what about this one? HClO4. How would you name this acid? Feel free to pause the video as you work out this example. So the first thing we need to do is identify the polyatomic ion. ClO4 minus is known as perchlorate. So all we need to do is replace the 8 part with ic. So this is going to be called perchloric, and then add the word acid to it. So perchloric acid. Now what about HClO? What's the name for this acid? So ClO is the polyatomic ion hypochlorite. So let's replace ite with is. So to name the acid, it's simply going to be hypochlorous acid. Now what about HCl? How can we name that acid? So the anion Cl- is known as chloride. Because it has an IDE ending, we need to add the prefix hydro, and then instead of saying chlorine, after the R we're going to add ic, so hydrochloric acid. Now we're going to work backwards. If you're given the name, how can you write the formula? For example, what is the formula for phosphoric acid? So notice that we don't have the prefix hydro, so that means that it's associated with a polyatomic ion. We need to replace ic with 8, so this is associated with the phosphate polyatomic ion. Phosphate is PO4 3-. Once you've identified the ion, you simply need to add hydrogens to it. Because the charge is -3, we need to add 3 hydrogens to it, so it's going to be H3PO4. So this is the formula for phosphoric acid. Let's try another one. Carbonic acid. So we don't have the prefix hydro, so it's associated with a polyatomic ion. So let's replace ic with 8. So we need to write the polyatomic ion carbonate. Carbonate is CO3 2-. And since it has a -2 charge, we've got to add 2 hydrogens to it. So the name of carbonic acid, or the formula for it, is H2CO3. Now what about this one? Hydrobromic acid. So because we have the prefix hydro and the suffix ic, it's associated with ide, or bromide. And bromide is a monoatomic ion, which is Br-. Because it has a -1 charge, we only need to add 1 hydrogen to it. So the formula for hydrobromic acid is simply HBr. Now what about iodic acid? What's the formula for it? So there's no hydro, so it's a polyatomic ion that contains oxygen, and if we replace the ic part with 8, it's associated with the polyatomic ion iodate. Now chlorate was ClO3-. Iodate is IO3-. The halogens, they follow a similar trend. So to write the formula for iodic acid, because we have a -1 charge, we only need to add 1 hydrogen, so it's going to be HiO3. Now here's the last one, acetic acid. So if we replace ic with 8, this is associated with acetate. Acetate is C2H3O2 -1. So we need to add 1 hydrogen to it. So the formula is HC2H3O2. So that's the formula for acetic acid. Now the next thing that we need to talk about in chemistry is grams, moles, atoms, things like that. Now, mass represents the quantity of matter, and in chemistry, mass is usually measured in grams. 1 kilogram is 1,000 grams. Now what about moles? What is a mole? The best way to understand what a mole is to compare it with a dozen. A dozen is simply a quantity. A dozen represents 12. A dozen eggs is 12 eggs. A dozen calculators, 12 calculators. A dozen is to 12 the same way as a mole is to a very large number, a number called Avogadro's number, which is 6.02 times 10 to the 23. So if you have a mole of pencils, you have 6 times 10 to the 23 pencils. If you have a mole of atoms, you have 6 times 10 to the 23 atoms. And so a mole is just a very large quantity. Now there's something called molar mass. Molar mass is the ratio between the mass and the moles. It's grams over moles. And in the periodic table, you'll see this number below carbon, which is 12.01, the average atomic mass of carbon, or you could simply say atomic mass. This is also the molar mass of carbon. And the units for molar mass is 12.01 grams per mole. So as you can see, molar mass is simply the mass divided by moles, grams over moles. Now let's say if you wanted to calculate the molar mass for CH4, how would you do it? All you need to do is add up the atomic masses for every atom in that molecule. Carbon has an atomic mass of 12.01, and for hydrogen it's about 1.008, but times 4 since we have 4 hydrogens. So let's round it and let's say this is 12 and hydrogen is 1. So the molar mass of methane is about 16 grams per mole. Calculate the molar mass for sodium hydroxide and for glucose. So the atomic mass for Na is 23, for oxygen is 16, for hydrogen is 1. So sodium hydroxide has a molar mass of 40 grams per mole. So what this means is that 1 mole of sodium hydroxide has a mass of 40 grams. So 2 moles of sodium hydroxide will have a mass of 80 grams. So molar mass is simply the ratio between grams and moles. Now what about the molar mass of glucose, C6H12O6? Now what's the answer? So there's 6 carbon atoms, each with an atomic mass of 12. There's 12 hydrogen atoms, which has an atomic mass of 1, and 6 oxygen atoms, each with an atomic mass of 16. 6 and 12 is 72, and 6 times 16 is 96. 72 and 12, that's 84, and 84 and 96, that's 180. So the molar mass of glucose is 180 grams per mole. So 1 mole of glucose has a mass of 180 grams. 2 moles of glucose has a mass of 360 grams. 3 moles of glucose has a mass of 540 grams. And you can see a pattern there. Now the next thing we need to talk about is mass percent. If you want to find the mass percent of an element in a compound, it's simply the mass of the element divided by the total mass times 100%. So for example, let's say if we want to find the mass percent of carbon in methane. So the atomic mass of carbon is 12. Now the total atomic mass is the mass of carbon plus the mass of the 4 hydrogen atoms times 100%. So it's 12 out of 16 times 100%. And so you're going to get 75% carbon. Now, if you want to find, let's say, the percent of hydrogen, it's going to be the mass of hydrogen, or the molar mass of hydrogen, divided by the total mass. 4 out of 16 times 100% is 25%. So it's 25% hydrogen, 75% carbon. Notice that the total percentage is 100%. So now it's your turn. Calculate the percent by mass of sodium in sodium hydroxide. So we know the molecular mass, or the atomic mass of sodium, is 23. The formula mass of the NaOH formula unit, we calculated that already. It was 23 plus 16 plus 1, which is 40. So at this point, if you type it in, 23 over 40 times 100, you should get a mass percent of 57.5%. So that's the percent of sodium in this compound. Now, how much, or what is the percent of hydrogen in sodium hydroxide? So the mass of hydrogen is 1 divided by a total molar mass of 40. So it's 1 out of 40 times 100. So it's 2.5% by mass for hydrogen. Now what about for oxygen? Since oxygen is the last element, we could simply do 100 minus 57.5 minus 2.5, or 100 minus 60. So that means that it's 40% oxygen, because the 3 percentages, they have to add up to 100%. So if you typed in 16 out of 40 times 100, you should get 40%. For the sake of practice, let's try another example. Let's use glucose. Find the mass percent of carbon in this compound. So the mass of carbon, there's 6 carbon atoms, so 6 times 12. That's the total molar mass of all the carbon atoms in glucose. Now the total molar mass for all of the atoms in glucose is 6 times 12 plus 12 plus 6 times 16 times 100%. So the 6 carbon atoms has a molar mass of 72. The molar mass of the entire compound is 180. And so now we just got to type these numbers in the calculator. And so it's 40% by mass for carbon. So now you know how to find the mass percent of an element within a compound. Now the next thing that we need to talk about is converting grams into moles. So for example, let's say if you have 48 grams of carbon. How many moles of carbon is this equivalent to? So whenever you want to convert from grams to moles or moles to grams, you need the molar mass. Based on the periodic table, the molar mass of carbon is 12. So what that means is that 1 mole of carbon has a mass of 12 grams. So let's convert. Start with what you have. Now since we have grams of carbon on the upper left side, we need to put grams of carbon on the bottom. So 12 is associated with it, and so 1 mole of carbon is going to go on top, so that these units cancel. So it's simply 48 over 12, which is equivalent to 4 moles of carbon. Now let's make sense of it. So the molar mass is 12, and as we mentioned before, 1 mole of carbon is equal to 12 grams. So 2 moles of carbon is equal to 24 grams. 3 moles of carbon is equal to 36 grams. So for every mole of carbon that you add, the mass increases by 12. So 4 moles of carbon equates to 48 grams of carbon, which is the answer that we wanted. Now, try this example. So let's say if you have 22 grams of carbon dioxide, go ahead and convert it to moles of CO2. So the first thing you need to do is find the molar mass of CO2. The atomic mass of carbon is 12, and for oxygen is 16, but there's 2 of them. So 16 times 2 is 32, plus 12, that's 44. So the molar mass is 44 grams per mole. So now let's start with what we're given, and we need to put grams on the bottom. So there's 44 grams of CO2 per 1 mole of CO2. So whenever you need to convert from grams to moles, take the mass in grams and simply divide it by the molar mass. So 22 divided by 44 is 0.5. So we have 0.5 moles of CO2. Now, if you need to go the other way, let's say if you want to convert from moles to grams, you need to multiply the moles by the molar mass. So let's say if we have 3 moles of neon, let's convert it to grams of neon. So let's start with what we're given. Now if you use the periodic table, if you take a look at it, you'll see that the atomic mass of neon is approximately, I'm going to round it, it's about 20 grams per mole. So there's 20 grams of neon per 1 mole of neon. So you want to set it up in such a way that the unit moles of neon cancels. And so since we have 2 numbers on top, we got to multiply. 3 times 20 is 60. So you're going to get 60 grams of neon. Try this one. Let's say if you have 5 moles of C2H6 molecules. Convert this into grams of C2H6. C2H6 is ethane. So let's find the molar mass first. So we have 2 carbons, each with an atomic mass of 12, and 6 hydrogens, each with an atomic mass of 1. So 2 and 12 is 24, plus 6 is 30. So it's 30 grams per mole. So let's start with 5 moles of ethane. Let's convert it to grams. So there's 30 grams of ethane per 1 mole of ethane. Therefore, the unit moles of ethane will cancel, and so it's 5 times 30. We know 5 times 3 is 15, so 5 times 30 is 150. You got to add the 0. So we have 150 grams of ethane. So that's how you can convert from moles to grams using molar mass. So if you want to write an equation, the moles is equal to, well, let's actually write it this way. Mass in grams is equal to the molar mass times the moles. So let's use lowercase m for mass, and let's use capital M for molar mass, and N for moles. Be careful though, capital M sometimes could be molarity, so watch out for that. So mass is molar mass times moles. Now let's say if you have 3 moles of carbon atoms. How can we convert that to the number of carbon atoms? So if you have 3 moles of carbon, how many atoms do we have? So to answer this question, we need to use Avogadro's number. 1 mole is equal to 6 times 10 to the 23. It's really 6.022 times 10 to the 23, but I'm going to round it to 6 times 10 to the 23. So let's start with 3 moles of carbon. 1 mole of carbon is equal to 6 times 10 to the 23 atoms of carbon. So that's how you can convert from moles to atoms. Simply multiply by Avogadro's number. So the answer is 6 times 3, that's 18. So it's 18 times 10 to the 23 atoms. Now, to put it in proper scientific notation, we need a number between 1 and 10. 18 is greater than 10. So let's move the decimal 1 unit to the left. Anytime you move the decimal 1 unit to the left, the exponent needs to go up by 1. So you have to add 1 to 23. So it's 1.8 times 10 to the 24 atoms of carbon. Now let's say if we have 4 moles of methane. How many molecules of methane do we have? And how many atoms of hydrogen do we have? So let's find molecules of methane. So methane is not an atom. You can't go directly from 4 moles of CH4 to atoms because this is a molecule. A molecule is a particle that is composed of many atoms. So when using Avogadro's number, 1 mole of methane corresponds to 6 times 10 to the 23, not atoms of methane, but molecules of methane, since CH4 is a molecule. So if we simply multiply 4 by 6 times 10 to the 23, that's all we need to do to get the molecules of CH4. So that's going to be 24 times 10 to the 23, which is the same as 2.4 times 10 to the 24 molecules of CH4. Now, if we want to find the atoms of hydrogen, we need to take it one step further. In 1 molecule of CH4, you need to realize that there's 4 atoms of hydrogen because of the subscript 4. So 4 times 6 is 24. 24 times 4. If 20 times 4 is 80, 4 times 4 is 16. 80 and 16 is 96. So 24 times 4 is 96. So it's 96 times 10 to the 23 atoms of hydrogen, which is the same as 9.6 times 10 to the 24 atoms. So this is the answer. So that's how you can go from moles to molecules to atoms. Now sometimes you may need to convert from grams to atoms. So let's say if you have 16 grams of helium, convert it to atoms of helium. Now helium is not a molecule, it's made up of atoms. So we don't need that extra step to go from molecules to atoms. But first, before we can go to atoms, we need to convert grams to moles and then moles to atoms. You can't go directly from grams to atoms. So to go from grams to moles, we need the molar mass. The atomic mass or molar mass of helium is about 4. It's 4 grams per mole. So 4 grams of helium equates to 1 mole of helium. So these units cancel, and now we can convert moles to atoms. 1 mole of helium is 6 times 10 to the 23 atoms of helium. So it's going to be 16 divided by 4, which is 4. 4 times 6 is 24. So 24 times 10 to the 23rd is 2.4 times 10 to the 24th atoms of helium. Now let's say if you have 3 times 10 to the 23 atoms of argon. And let's say you want to convert that to grams of argon. Try that example. So first, we need to convert atoms into moles. And we can use Avogadro's number. So 1 mole of argon atoms is equal to 6 times 10 to the 23 atoms. So the unit atoms cancel, and now we can go from moles to grams. The molar mass for argon is about 40. So there's 40 grams of argon for every mole of argon. So those units disappear. So now let's do the math. We can cancel the 10 to the 23rds because they're the same. 3 divided by 6 is a half, and half of 40 is 20. So the answer is 20 grams of argon. So now you know how to convert from atoms to grams. Now let's switch gears and go to reactions. You need to be able to classify the different types of reactions, and you need to know how to balance it. So let's start with combustion reactions. So let's say if you have propane, which is C3H8, and we're going to react it with oxygen gas. If you see carbon, hydrogen, and oxygen, this is going to be a combustion reaction. The products of a combustion reaction are typically CO2 and water. Now, to balance a reaction, your goal is to make sure that the atoms on the left side and on the right side are the same. And to make it equal, you can modify the coefficients of the reaction. The coefficients are the numbers in front of the substances. The subscripts are the small numbers, like the 3, the 8, the 2. Those are the subscripts. You can't change those when balancing the equation. You can only change it when writing a formula, but when you're balancing an equation, you can only add subscripts. I mean, not subscripts, but coefficients, which are the number in front of these molecules. When balancing a combustion reaction, the first thing that you want to do is balance the carbon atoms. So we have 3 carbon atoms on the left, therefore we got to put a 3 in front of CO2. Now the next thing you want to move to is the hydrogen atoms. We have 8 on the left, 2 on the right. 8 divided by 2 is 4. So let's put a 4 in front of H2O. Now you want to save the oxygen atoms for last. So 3 times 2 is 6, so we have 6 oxygen atoms in the 3 CO2 molecules. 4 times this invisible 1 is 4, so we have 4 oxygen atoms in the 4 water molecules. 6 in 4 is 10, so we have a total of 10 oxygen atoms on the right side. So what number do we need to put in front of O2 to balance it? Well, 10 divided by the subscript 2 is 5. So we need a 5 in front of O2. And since we don't need a number here, we could put a 1. And now the reaction is balanced. We have 3 carbon atoms on both sides, 10 oxygen atoms, and 8 hydrogen atoms on both sides. So that's how you can balance a combustion reaction. Now let's try another example. C2H5OH, which is known as ethanol, plus O2, produces carbon dioxide and water. Go ahead and balance this particular combustion reaction. So notice that we have 2 carbon atoms on the left side. We need to put a 2 in front of water. And we have a total of 6 hydrogen atoms. 5 plus 1 is 6. 6 divided by 2 is 3, so we need to put a 3 in front of H2O. To notice that we have 4 oxygen atoms from the 2 CO2 molecules and 3 oxygen atoms from the 3 water molecules. 4 plus 3 is 7. Now notice that we already have an oxygen atom in ethanol. So what number do we need to put in front of O2? Since we already have one oxygen atom on the left side in ethanol, we need 6 oxygen atoms from the O2 molecule, because 1 plus 6 is 7. So 6 divided by the 2 is 3. Therefore, we need to put a 3 in front of O2. So notice that we have a total of 7 oxygen atoms on both sides. So we have 4 and 3, which is 7, 1 and 3 times 2, which is 6, so 6 and 1 is 7. So everything is balanced. We have 2 carbon atoms on both sides, 6 hydrogen atoms, and 7 oxygen atoms. By the way, are combustion reactions considered to be redox reactions? What would you say? Consider this reaction. Butane plus oxygen produces CO2 and water. Here's another combustion reaction. It turns out that every combustion reaction is a redox reaction. A redox reaction is simply a reaction where electrons are being transferred from one element to another. A quick way to determine if a reaction is a redox reaction is to look at the substances in the reaction. On the left side we have the reactants, on the right side you have the products. If you see a pure element on one side of the reaction and that element in the compound, then it's a redox reaction. So here we have a pure element and here's a compound. If you see that, it's definitely going to be redox. Now how would you balance this combustion slash redox reaction? So let's start with the carbon atoms. We have 4 on the left, so we need to put a 4 in front of CO2. Now we have 10 hydrogens on the left side. 10 divided by 2 is 5, so we need to put 5 in front of H2O. Now how many oxygen atoms do we have on the right side? So we have 8 and 5, which is 13. 13 divided by 2 is 13 over 2. So notice that we have a fraction. Whenever you get a situation like this, simply multiply everything by 2. So it's going to be 2 C4H10. Now 13 over 2 times 2, the 2's cancels and you're just going to get 13. So it's going to be 13O2 and then 8 CO2 plus 10 H2O. So notice that the reaction is now balanced. We have a total of 8 carbon atoms, 20 hydrogen atoms, 10 times 2 is 20, and 26 oxygen atoms. 8 and 2 is 16, plus the 10 from water, that adds up to 26. So everything is balanced in this particular reaction. Here's a reaction for you. When zinc is mixed with elemental bromine, what's going to happen? What product will be produced? This is a combination reaction. If you mix A and B and you get a single product, that's known as a combination reaction. Not every combination reactions are redox reactions. Some are, some are not. Now, if you mix a metal and a nonmetal, these two will react in such a way to produce an ionic compound. Zinc is going to give up its electrons, and it's going to turn into the zinc plus 2 cation. Bromine is going to acquire the electrons, and it's going to turn into bromide. To write the formula of the product, simply use the crisscross method. So it's going to be Zn1 Br2, which we're simply going to write ZnBr2. And the reaction is already balanced. So is this reaction a redox reaction? Notice that we have zinc as a pure element and zinc within a compound. So when you see that, a pure element on the left, compound on the right, or vice versa, it's a redox reaction. Now, which substance is oxidized and which substance is reduced? So you need to look at something called oxidation states. The oxidation state of any pure element is always 0. Now, in zinc bromide, we know that zinc has a +2 charge. elemental bromine has an oxidation state of 0. But bromide, and zinc bromide, individually has an oxidation state of -1 because bromide typically forms a -1 charge. Whenever the oxidation state increases, the substance is oxidized. So the oxidation state of zinc went from 0 to +2. So zinc was oxidized. The substance that is oxidized is always a reactant, never the product, so it's always on the left side. Now bromine was reduced. Notice that the oxidation state decreased or was reduced from 0 to -1. So Br2 was reduced. The substance that is oxidized is known as the reducing agent, and the substance that is reduced is the oxidizing agent. Zinc is the reducing agent because it caused the other substance, bromine, to be reduced. Bromine is the oxidizing agent because it caused the other substance, zinc, to be oxidized. Metals, most metals, particularly the active ones, are usually good reducing agents because they like to give away electrons. Nonmetals like bromine are oxidizing agents because they like to take away electrons. Whenever a substance gives away or loses electrons, it is oxidized. A substance that receives or gains electrons is said to be reduced. Now let's say if we were to mix calcium oxide and water. Calcium oxide is a basic anhydride. Metal oxides are considered basic anhydrides because when you add them to water, they turn into a base. Calcium oxide reacts with water to produce calcium hydroxide. Whenever you see a metal with an OH, it's a base. Bases produces hydroxide ions in solution. So notice that this is a combination reaction. It's in the form A plus B turns into AB. Now this particular combination reaction, which is already balanced, is it a redox reaction or is it not? Notice that there's no pure elements in this reaction. We have a compound, compound, compound. If you don't see a pure element, it's safe to say this is not a redox reaction. So there's no transfer of electrons in this reaction. Now let's say if you were to have calcium carbonate, and if you add heat to it. Metal carbonates, they decompose when you add heat. This is going to turn into calcium oxide, and it's going to release a volatile component that is contained in calcium carbonate. That volatile component is carbon dioxide gas. Whenever you add heat, if a gas can escape, it will escape. Now what kind of reaction do we have here? So we have the reverse of a combination reaction. We have a larger product breaking down into two smaller components. So this is known as decomposition. Now, is it redox or is it not a redox reaction? Notice that we have a compound, compound, compound. No pure elements. So it's not a redox reaction. Now let's say if we have magnesium nitride, which is a solid. If we add heat to it, what's going to happen? Typically, whenever you add heat to a compound, if it's enough, if it's like a lot of heat, it can decompose. If there's a gas that can be produced, then the formation of the gas is going to drive the reactions to the right, making it spontaneous. When you heat magnesium nitride, it's going to turn into magnesium metal and nitrogen gas. Nitrogen gas is very stable, so heat is going to drive the reactions to the right, producing this volatile gas. To balance it, we simply need to put a 3 in front of Mg. So is this a redox reaction or is it not? So we know this is a decomposition reaction. We have a compound breaking into its elements, and it turns out it is a redox reaction. Here we have a compound, and here we have a pure element. So it's a redox reaction. Now there are some other common decomposition reactions that you should know. The decomposition of potassium perchlorate, if you add heat to it. This breaks down into potassium chloride and oxygen. Another one is mercury oxide, which is a solid. If you add heat, it's going to turn into mercury metal, which is a liquid, and you're going to get oxygen gas. So notice that heat favors the formation of a gas. If a gas can be formed, it's going to drive the reaction to the right, making it spontaneous. So both of these are decomposition reactions. Now, are they redox reactions? If you look at the first one, we have a compound, and here we have a pure element. So it's a redox reaction. For the second one, compound, pure element, redox. To balance the first one, notice that we have 3 oxygens on the left, 2 on the right. The least common multiple of 2 and 3 is 6. So to make them equal, we need to get 6 oxygen atoms on both sides. So we need to put a 2 in front of KClO3 and a 3 in front of O2. So we have 6 oxygen atoms on both sides. Notice that we have 2 potassium atoms, so we got to put a 2 in front of KCl. Now it's balanced. For mercury oxide, all we got to do is put a 2 and a 2, and it's balanced. So we have 2 mercury atoms and 2 oxygen atoms. Now we said that whenever you have a metal oxide with water, it's going to produce a base. So metal oxides are basic anhydrides. Now what about non-metal oxides, like sulfur dioxide? Non-metal oxides are acid anhydrides because when you put them in water, they will turn into an acid. SO2 plus water turns into H2SO3. If you put sulfur trioxide in water, it's going to turn into sulfuric acid. If you mix carbon dioxide with water, it turns into carbonic acid. So as you can see, non-metal oxides are acid anhydrides, metal oxides are basic anhydrides. Now, let's say if you have calcium hydroxide. If you add heat, you're going to get the reverse reaction of what we had in the last example. This is going to break down into calcium oxide and water. Now, depending on the temperature, water can escape as a liquid, or if it's hot enough, it could leave as steam. Now, let's say if you have a single replacement reaction. Zinc plus, actually, let's change it. Let's make it aluminum plus hydrochloric acid. What are the products of this single replacement reaction? Aluminum is going to displace hydrogen out of the solution, and it's going to pair up with Cl. Aluminum is going to lose its 3 electrons, turning into the aluminum plus 3 ion, and chloride usually has a -1 charge. So using the crisscross method, when these two get together, they turn into AlCl3. Now when hydrogen is displaced out of the solution, it's going to be elemental hydrogen, which is diatomic, and it's going to leave as gas. Aluminum is a solid. HCl is aqueous, which means that it's dissolved in water. Aluminum chloride will also be in the aqueous phase. So in this reaction, we're placing a solid chunk of aluminum in a solution of HCl, which means the HCl is mixed with water. So whenever you see AQ, that means that it's dissolved in water. Now, this single replacement reaction, is it a redox reaction? It turns out that all single replacement reactions are redox reactions. Notice that we have a pure element and a compound, so it's a redox reaction. Now, which substance is oxidized and which one is reduced? So aluminum is in the 0 oxidation state because it's a pure element, but in its compound is +3. Now hydrogen is in the +1 oxidation state because chlorine is -1. Whenever hydrogen is bonded to a nonmetal, it usually has a +1 charge, but when it's bonded to a metal, it usually has a -1 oxidation state or charge. Now elemental hydrogen is 0. So aluminum goes from 0 to 3. So the oxidation state goes up. So aluminum was oxidized. Now hydrogen in HCl, it went down, or it was reduced from 1 to 0. So HCl was reduced. Since aluminum was oxidized, aluminum is also known as the reducing agent. hydrogen was reduced, so it's called the oxidizing agent. So as we can see here, most active metals are reducing agents, and nonmetals are usually oxidizing agents. Going back to this reaction, a quick way to distinguish a single replacement reaction from, let's say, a double replacement reaction is this method. In a single replacement reaction, typically you have an element reacting with a compound. When you see that, it's usually a single replacement reaction. By the way, how would you balance this reaction? What would you do to balance it? So notice that we have 3 chlorine atoms. So we're probably going to have to put a 3 in front of HCl. But notice that we have an odd number of hydrogens and an even number over here. The least common multiple between 3 and 2 is 6. So that tells us that we need 6 hydrogen atoms. So let's put a 3 here to make it 6, and let's put a 6 there. And let's rebalance it. So now that we have 6 hydrogen atoms on both sides, let's balance the chlorine atoms. We have 6 on the left, 3 on the right, so we need to put a 2 in front of AlCl3. And so since we have 2 aluminum atoms on the right side, we got to put a 2 in front of Al. Now the reaction is balanced. Now consider this reaction. Let's say if we have an aqueous solution of silver nitrate plus magnesium chloride, and we want to find out what the products for this reaction will be. Nitrates are always soluble, so this is going to be aqueous. To know this, you need to understand the solubility rules. Nitrates, acetates, ammonium, which is NH4+, are always soluble. Alkali metals like lithium, sodium, potassium, rubidium, they're always soluble. The halides like chloride, bromide, iodide are generally soluble except with silver, lead, and mercury. So with magnesium, chloride is soluble. Now this is a double replacement reaction. We have a compound reacting with a compound. In a single replacement reaction, it's an element plus a compound. In a double replacement reaction, the 2 groups on the outside are going to pair up together, and the 2 in the middle are going to pair up. So Ag is going to pair up with Cl. So we have Ag1 and Cl minus 1. Because these 2 have the same charge, even though the sign is opposite, we can write them in a 1-to-1 ratio. Now, chloride is soluble with everything except silver, lead, and mercury. So silver is an exception. So this is a solid. Whenever you mix 2 aqueous solutions together, and if you get a solid product, this double replacement reaction is also known as a precipitation reaction, which is what we have in this particular case. And now we need to find the other product. So let's pair up magnesium with nitrate. Magnesium is an alkaline earth metal with a +2 charge, and nitrate is a polyatomic ion with a -1 charge. Using the crisscross method, we could see that it's Mg1NO32. Whenever you have multiple polyatomic ions, make sure you enclose the polyatomic ion within the parentheses. Now, we said nitrates are always soluble, so magnesium nitrate is going to be aqueous. So now what we need to do at this point is balance the reaction. So we have 2 nitrates on the right side, so we got to put a 2 in front of AgNO3. And we have 2 chlorines on the left side, so we need a 2 in front of AgCl. And now the reaction is balanced. Now this particular double replacement reaction, would you consider it a redox reaction? What would you say? Notice that there's no pure element in this compound. I mean, not compound, but there's no pure element in this reaction. This is a compound, that's a compound, compound, compound. So double replacement reactions are never redox reactions because you won't see any pure elements in this reaction. Now typically with double replacement reactions, you need to be able to write the net ionic equation. How can we do that in this particular example? The first thing that you need to do is write the total ionic equation. So everything that is in the aqueous phase, we need to separate it into ions, except the solid. So we have 2 Ag plus ions and 2 nitrate ions in AgNO3. In this compound, MgCl2, we have a magnesium ion and 2 chloride ions. AgCl is a solid, so we're going to leave it that way. Everything that we separate into ions, all of these are in the aqueous phase, by the way. And then magnesium nitrate, we could separate that into Mg plus 2 or Mg2 plus and 2 nitrate ions. If you're submitting this into an online assignment, typically, instead of writing plus 2, you may have to write 2 plus. Now, this is the total ionic equation. Our next step is to eliminate the spectator ions. The spectator ions are those that do not participate in the reaction. They just spectate, they watch. So, on the reaction, they look exactly the same. The nitrate ions are spectator ions. We can cancel them out. And magnesium is a spectator ion. So what remains is the net ionic equation, which is 2Ag plus 2Cl minus produces 2AgCl. Notice that each of these has a coefficient of 2, which means we could divide each one by 2. So it simplifies to this: Ag plus, which is in the aqueous phase, and Cl minus, which is also in the aqueous phase. These two will react to produce solid silver chloride. So this is the net ionic equation for this example. Now let's try another double replacement reaction. What's going to happen if we mix sodium hydroxide with sulfuric acid? So this is an acid-base neutralization reaction. When you mix a strong base with a strong acid, they will react to produce salt and water. But it's still a double replacement reaction, which means it's not a redox reaction. So the two on the outside will pair up. Sodium has a +1 charge, and sulfate has a -2 charge, which is important for you to know the polyatomic ion list, because without that, you won't be able to write the correct formula for sulfate if you don't know the right charge, and you won't be able to write the net ionic equation. So you have to make sure you know your polyatomic ions. So if we pair these two ions together, it's going to be Na2SO4 1, or just SO4. So that's one of the products that we have. To find the other product, whenever you pair H with OH, these two will just create water. This is something that you should just know or commit to memory. So now we have a balanced reaction. Well, we just have a reaction, but we got to balance it. So notice that we have 2 sodium atoms on the right side, so we got to put a 2 in front of NaOH. Now to balance acid-base reactions, here's what you can do to quickly get the answer. Notice that you have 2 hydroxide ions, 2 H plus ions. That's going to produce 2 water molecules. It's always going to work out that way. So this is a 1. So now the reaction is balanced. So before we can write the net ionic equation, we need to write the phases of every substance. So typically the stuff on the left for a double replacement reaction is usually in the aqueous phase. Sodium hydroxide is soluble in water. Na is an alkali metal. Alkali metals are always soluble. Now acids, for the most part, are soluble in water. I've never seen an acid that doesn't dissolve in water. And water is a liquid. So to write the total ionic equation, everything that's in the aqueous phase, we need to separate it into ions. So we're going to have 2 Na plus ions from NaOH and 2 hydroxide ions. Now in the next compound, sulfuric acid, we have 2 H plus ions and 1 sulfate ion. In sodium sulfate, there are two sodium ions and a sulfate ion. And water is a liquid, so it's not aqueous. Therefore, we need to leave it the way it is. So what are the spectator ions in this total ionic equation? So which ions look exactly the same on both sides? So that's sodium, and so now we can write the net ionic equation. But notice that we have two hydroxides, 2H plus, two water molecules. So every coefficient is 2. Let's divide the coefficients by 2. So it's going to be 1 hydroxide, which is in the aqueous phase, plus 1H plus ion, or hydrogen ion, in the aqueous phase. And this is going to produce liquid water. So this is the net ionic equation for this acid-base neutralization reaction. So that is it for this video. By the way, look out for my other videos on YouTube, particularly the ones on stoichiometry. I've created one that's entitled Stoichiometry, Grams, Moles, Atoms, Molecules. It also has examples on limiting and excess reactants, percent yield, theoretical yield, things like that. And I've created another one on solution stoichiometry where it goes over molarity calculations and how to convert from grams to moles to molarity to liters and things like that, and how to do dilution problems using the M1V1 equals M2V2 equations. So take a look at those videos when you get a chance. It continues from where we left off. And that's all I got for today, so thanks for watching. I hope you found this video to be educational, and have a great day.